Today, I'd like to talk about vector-valued functions. In contrast to the kind of things we already know about functions, where a number is fed into a procedure and then a number comes out, such as this function, instead, we're going to think about functions where the input is a number, but what comes out as a result isn't. It's a vector instead. These new functions will indicate by a letter, as we usually do, but we'll put a little arrow above the letter to remind ourselves that the output is a vector. The input, for now, we'll just call it t. If I were working a physics problem, the t might very well be time, and this vector might indicate where I'm located at. For instance, here, the 2t plus 1 would give me the x-coordinate, and the t squared would give me the y-coordinate that goes with a certain value of t. A number n, 0, 2 times 0 plus 1 is 1, 1 times I. 0 squared is 0, j, gives a single vector out. So obviously for this particular one, you could put any value of t in that you care to put in. As usual, we'll call the domain of this function the set of all t numbers that are allowed to be put into the function. We can always evaluate 2t plus 1 and t squared, so unless there's a reason to restrict the domain, we'll say that the domain of this particular function is all real numbers. T can be any real number. The range is more difficult to think about. The range is the collection of all the vectors that you could get by evaluating R. If I draw in a few of these vectors, I can see that I can represent this function with such a picture. I do have a problem though. There's going to be an unlimited number of different t values, and if I plotted all of the vectors that went with them, I would end up with pieces of the plane just completely covered up in ink. The easiest way to visualize this is to do what's called eliminating the parameter, thinking of this as being the x-coordinate of a point, and that as being the y-coordinate. Y is t squared. T is the same thing as x, though, so y is the same thing as x squared. This takes the vector-valued function and expresses it in a more familiar way to us. Y equal x squared is a parabola. The vectors involved in the vector-valued function are going to be all of the arrows that start at the origin and end on the parabola. So even just drawing a few vectors in, you can see that it's going to cover up regions of the plane completely in black, and this won't tell me anything. For this reason, what people often do is they'll just plot the end points of the vectors instead. So for example, x equal negative 2, y equal 4, x equals negative 1, y equal 1, x equals 0, y equals 0, x is 1 and y is 1, and x is 2 and y is 4. It's customary, if you're going to draw the graph of a vector-valued function like this, that you include little arrows that indicate the increasing t direction. So as t increases from negative 2 to negative 1 to 0, 1, then 2, we're going in that way. Sometimes a little care has to be taken. In the vector-valued function r of t equals t squared I plus t to the fourth power j, it is true that the y-coordinate is the square of the x-coordinate, but if you look at the equation that tells me x, x is the square of a real number, x can't be negative. So to say that the graph of the vector-valued function is going to be represented by the graph of y equal x squared isn't altogether true. The x needs to be bigger than or equal to 0. On this graph, for instance, when t is negative 2, x is 4 and y is 16. When t is negative 1, x and y are both equal to 1. When t is 0, you're at the origin. So you have approached the origin from a point that's up in the first quadrant down to the origin. But then, when t is 1, x is 1 and y is 1 as well, and you're back at this spot again. And when t is 2, x and y are 4 and 16 again. What's happened is, negative t numbers approaching 0 approach the origin, and you eventually get there at t equals 0, and then immediately turn around and start going right back out along that same half of a parabola. So if I just said the graph looked like y equal x squared, I would be lying a little bit, because on the actual graph of the vector-valued function, there aren't any negative x values. In the vector-valued function r equals 5 cosine t plus 5 sine of t, we can eliminate the parameter and write the graph as though we were back in Calculus 1. If the x-coordinate is 5 cosine t, then obviously cosine of t is x divided by 5, and likewise this tells me that sine of t must be y over 5. No matter what the value of t is, cosine squared of t plus sine squared of t is always 1, so that means that this number squared plus that number squared always has to be 1. That tells me that x squared plus y squared has to be 25, and everyone will remember that this is a circle centered at the origin of radius 5. What this equation doesn't tell me, though, is how these points are traced out. So if I think of t as being 0, x would be 5 and y would be 0. T equals 0 is here. If I think of t being pi over 2, x will be 5 times cosine pi over 2, which is 0. Y will be 5 times sine pi over 2, which will be 5. As t increases from 0 to pi over 2, I go from being here to being there. If t is equal to pi, x will be negative 5 and y will be 0, which is here. So I'm continuing to travel in the same direction. If you put 3 pi over 2 in, you'll find that you're here, and when t is 2 pi, you're back where you started. So as we said, we'll draw little arrows in on our picture to indicate which direction we're going in. In this picture, if I had drawn in all of the vectors with their initial and terminal point, it would completely cover up the interior of this disk, and that would tell me very little. You can also have vector-valued functions that give results that are in three-dimensional space. As a simple example of that, let r equal 5 cosine ti plus 5 sine tj plus t times k. If the last term wasn't there, we would be back in the previous situation. When t is 0, the z-coordinate is going to be 0, and as t increases, it will become positive. If you start at 0 and decrease t, you'll get negative z-coordinates. The resulting graph from above would look like a circle, but viewed from a sideways perspective, you can see that it's actually a helix. I've only drawn in positive t values because the picture gets hard to understand otherwise. As a prelude to being able to do differential and integral calculus to these type of functions, we need to say a few words about limits and continuity. For our present purposes, I'm going to think of having vector-valued functions whose x part is f of t, y part is g of t, and if I'm in 3 dimensions, the z part will be h of t. We really should have an epsilon delta type argument for the definition of a limit, but in the particular case that we're working in our course, we can simplify the situation somewhat. If this limit, that one, and that one all exist, then we write in those values we get, and we call that the limit as t approaches c of the vector-valued function. If even one of these limits fails to exist, then we say that this limit doesn't exist. As an example, think about r of t being sine of t over ti plus e to the 2t minus 1 over t j. If you look at the two functions individually, sine of t over t and e to the 2t minus 1 over t, thinking about this from the Calculus 1 perspective, both of those functions are perfectly nice for all t values except t equals 0. R of 0 is undefined. What I'd like to investigate is, if t is allowed to get real close to 0, do the resulting vector values approach some particular vector or not? Does the limit exist? Since t equals 0 is the only place where this function can potentially be badly behaved, let's look at the limit as t approaches 0 of this. The first limit, the limit as t tends to 0 sine t over t, should be familiar to you from Calculus 1, but if it isn't, since the top tends to 0 and so does the bottom, it's an indeterminate form of type 0 over 0, and so is this limit. We can do these limits by L'Hopital's rule then. L'Hopital's rule, under these circumstances, says take the derivative of the top and bottom and see how that behaves. The derivative of sine is cosine. The derivative of t is 1. Cosine divided by 1 is cosine, and the limit as t goes to 0 of cosine t is cosine 0, is 1, because the cosine function is continuous for all inputs. In an exactly similar way, the other limit works out to be 2. Even though r at 0 is undefined, if t is very close to 0 but not equal to it, r of t will look very much like I plus 2 times j, or x equal 1, y equal 2, thinking of coordinates. The curve that represents the graph of the vector-valued function is perfectly nice near t equals 0, except it's missing a single individual dot that would correspond to t equals 0. In the language of Calculus 1, we would say that this is a removable discontinuity. To finish up this short video, The notion of continuity is just as it was back in Calc 1. A function is continuous at, in this case, t equals c, if three things are true. Firstly, r evaluated at c has to make sense. You actually have to get an answer out of it. Number two, the limit as t approaches c of r of t has to make sense as well. There's a hidden side catch to that, which I've indicated with the asterisk. We'll come back to that in a second. And thirdly, the value of the function, r of c, and the limit as t approaches c have to be the same thing. This is a very fancy way of saying if I had a three-dimensional marker, I could draw the entire graph near t equals c without picking my pen up. That leads directly into the asterisk, though, because there are some strings attached to this statement. For the limit to make sense, I have to be able to look at function values, r of t, for all t that are close to but not equal to c. That means there must be an interval of t numbers, which contains t equals c, upon which I'm guaranteed to be able to evaluate the r function, except maybe right at c. This is a slightly trickier looking statement than it actually is. But to cut to the chase, everything that was true about continuity in Calculus 1 will be true of them in this setting. The next thing that I want to talk about, obviously, if you think back to Calc 1, having talked about functions, domains, graphs, limits, and continuity, the next thing we're going to talk about is obviously derivatives and integrals. I hope everybody's having a good day. I'll talk to you again soon.